Today, let us look at a program to generate a square wave using timer. Let's look at the question. Generate a square wave of 75% duty cycle using timer. So in this program, no exact time delay is given, that is the time period or frequency of the square wave is not given. What is required is that the duty cycle should be 75%. For that, the on time or the high time should be 3 times the off time. So that is the only constraint that is specified in the question. Since an exact time period or frequency is not given, we have the freedom to choose whatever initial value to be loaded into the timer to generate the delay. That is, the off time can be any value. The only thing to be careful about is that the on time should be 3 times the off time, or the high time should be 3 times the low time. So now let's look at the program. The first step needed in this program is to select a mode for the timer. So let us select mode 1 for timer 0. Let's see the T mode register. Its bit pattern is gate CT bar M1 M0, gate CT bar M1 M0. The upper nibble is for timer 1, lower nibble is for timer 0. Since we are not using timer 1, all the values corresponding to timer 1 should be 0. And since we are not using an external control, gate should be equal to 0 for timer 0. And since there is no external clock pulse involved, CT bar should be equal to 0 for timer 0. Then we should select mode 1 for timer 0. So M1 M0. D1 D0 of T mode register should be 0 1. So the value to be loaded will be 7 zeros followed by 1. That is the binary pattern that should be loaded into T mode register. The hexadecimal equivalent of this value will be 01H. So the first instruction is move TMOD comma hash 01H. Before going to the next step, let's decide how we are going to generate the delay. In this program, it is beneficial for us to generate the delay using a subroutine instead of incorporating the delay into the main program. So we will write a delay subroutine with the name delay, and the delay generated by the subroutine will be equal to 1 off time. It will be equal to 1 off time. Now let's see what should be written in the main program. The only timer related step that is needed in the main program is selection of the mode that we have already done. The remaining instructions will be written in the subroutine. So now what should we do to generate a square wave of 75% duty cycle? We should select the pin on which the wave will appear. So let us select P1.7. The next step is to make P1.7 high. So the instruction to make P1.7 high is set bit P1.7. So the effect of this instruction is that P1.7 will be at logic 1. Now we should call the delay 3 times. Provide 3 delays. That is the next step. For that we can use the A call delay instruction. A call delay. The word that is shown in blue color is the name of the subroutine or the label of the first instruction of the subroutine. So A call delay, delay is a label. That label is the label of the first instruction of the subroutine. To call a subroutine, there are two instructions available in 8051's assembly language, A call and L call. A call is a 2-byte instruction and L call is 3-byte instruction. Since we are dealing with a small program, we will use A call because it also provides us the advantage of occupying only 2 bytes, whereas lcall would have occupied 3 bytes. The advantage of lcall is that it can jump larger distances. It can access a subroutine that is much farther away from the main program. But since that is not required here, we are using acall instruction and it has the advantage of taking up 1 byte less. The acall delay instruction has to be repeated 3 times because the delay we are creating in the subroutine is equal to 1 off time. And since our pin is now high, it should remain high for 3 delay times. So after executing this instruction, the effect is that P1.7 will remain high for 3 delay times. What is the next step? We should make P1.7 low. So the instruction for that is clear P1.7. That will make the waveform go low. The effect is as shown in the figure. Now the waveform has gone to a low value. P1.7 is at logic 0. What is the next step? The next step is to provide a single delay. The off time should be equal to 1 delay time. Provide 1 delay and the instruction is again acall. Acall delay. 1 delay will be called and the effect will be as shown. So now we have completed one entire cycle of our 75% duty cycle square wave. What is to be done next? The square wave is a continuous waveform, so we have to continuously repeat these steps to generate a square wave. So to repeat, what is the instruction? We should jump to the required instruction and continuously loop. The instruction to be used for that is sjump L1. And where should the label L1 be given? Which instruction should get the label L1? We need not include move tmode comma hash 01h because the mode has been selected and it has not been changed and there is no need to change it also. So that instruction need not be repeated. Now look at the waveform. It has now completed one cycle. Now for the next cycle the pin should go high. So L1 should be the label of the instruction that makes the pin go high, that is set bit P1.7. So we will give L1 as the label of set bit P1.7. The effect is that the pin goes high. Now after this instruction 3 delays will be called, then the pin will be cleared, 1 delay will be called and repeat. This continues and we will get a continuous square wave of 75% duty cycle on P1.7. Now let's write the delay subroutine. Since we wrote the main program first and we have used the word delay to call the subroutine, to access the subroutine, the label of the first instruction of the subroutine should be delay. Only then will this subroutine be called when you execute this instruction in the main program. These two, the operand of the acall instruction and label of the first instruction of the subroutine should be the same. That is when the call to the subroutine will work. So the first step is we gave the label delay as the label of the first. That's where we are going to write the first instruction of the subroutine. Now we have to use the timer to generate this delay. And if we look at the programming steps for the timer, we have only completed one step. That is, we have selected the mode for the timer. The remaining steps have to be written inside the delay subroutine. The next step is to initialize the timer registers TH0 and TL0. Let us choose the value FFFA for the timer. So move TH0, hash 0FFH will load FF into TH0. We used 0 so that the assembler will not mistake this numeral for a label. For all numbers that start with an alphabet, we should precede it with a 0 so that the assembler will not mistake it for a label and recognize it as a number. Now move TL0, hash 0 FAH will load FA into the TL register, TL0 register. Now the bit pattern in the timer. Timer is a digital counter. In case of 8051, it is a 16-bit counter. So the pattern, binary pattern inside the timer will be as shown in the figure. A set of 12 ones followed by 1010 FFFA. This is the initial count in the timer. Now what is the next step? The next step is to start the timer. Once we have loaded the initial count, we should start the timer. The instruction for that is set bit TR0, where TR0 is the run control bit of timer 0. It should be set to 1 so that the timer will get the clock pulse. Now let's give that instruction, set bit TR0. From this instant onwards, that is whenever set bit TR0 is executed, from that instant onwards, the timer will get the clock pulse and it will start to count up. 8051's timers count up. So from this instant onwards, it will start counting up. Once we start the timer, the next step is to monitor the timer overflow flag. The timer overflow flag will be 0 initially. TF0 is equal to 0 initially. Now, to monitor this flag, what should we do? We should use the JNB TF0 relative address instruction. Let's use JNB TF0, L2. Since we have already used L1 in the main program, we should use a different label here. So JNB, what does JNB do? If the specified bit is not 1, it will jump to the relative address. Jump on no bit. If TF0 is not 1, it will jump to L2. So initially TF0 is not 0, so this instruction will cause a jump to L2. So where should we give the label L2? Which instruction should get the label L2? The same instruction, because as long as TF0 is 0, we should remain here. We should wait here until it sets. Until TF0 becomes equal to 1, we should continuously monitor TF0. So JNB TF0 L2, L2 is the label of the same instruction. If TF0 is 0, there will be a jump to L2, which is the same instruction. Again TF0 will be checked, again 0, then L2, 0, L2. It will continuously loop here. And meanwhile, the timer is counting up. So the initial count is FFFA. After the first clock pulse, it will be FFFB, FFFC, FFFD, and look at TF0, all these while it is at 0. FFFE, FFFE. Now also TF0 is equal to 0. But when the next clock pulse occurs, that is when the timer rolls over to all zeros from the maximum count to the minimum count, TF0 will be set. TF0 becomes equal to 1. Now the jump to L2 will not occur because this condition is not true. Now the jump on no bit cannot be executed. The flag is set. So the instruction following the JNB instruction will be executed. The program execution will not be transferred to L2. What should we write here? What should we write here? In the first program that we learned in the timer, that is the 50% duty cycle square wave program, we would change the port pin here. We complemented the port pin here. But in this program, we have taken care of the port pin in the main program. We have made it 1 and 0 in the main program. So the delay subroutine is only to provide the delay. It will not modify the port pin. We need not write any port pin related instructions here. So what should we do next? The delay has been provided. We have waited until the flag is set. So enough time has elapsed. So what should we do next? We should stop the timer and clear TF0. This clear TF0 step is very important. If we miss this step, the next time the delay subroutine is called, this flag will be set. And if this flag is set, then it will not wait here, it will directly come to the next step. So after the flag is set, we should make sure that it is cleared for the next round of operation. So after JNB TF0, we should give the instruction clear TR0 to stop the timer and clear TF0 to clear the timer overflow flag. Now when this instruction is executed, TF0 becomes 0. Also note that the count now in the timer will be all zeros. That is, the value of TH and TL registers are all zeros. The value inside, that is TH0 will contain 00H, TL0 will contain 00H. Now, what is the last instruction to be given to the delay subroutine? Now we have written everything that is necessary to provide the delay, and we have made everything ready for the next round of operation also. So we are done with the subroutine. So the last instruction of the subroutine should be the return instruction. So let's give it here. When this return instruction is executed, program execution will be transferred back to the main program. When the first ACALL delay instruction is executed, program execution will be transferred to this location. These set of instructions will be executed. We will get the required delay, and after that, when the return instruction is executed, program execution will be transferred back to the main program. And to which instruction should it go? The next instruction that will be executed will be the instruction following the call instruction. So the second ACALL delay instruction will be executed next, and it will continue. So this is all that is required to generate a square wave of 75% duty cycle. Please note the advantage of using the delay subroutine. Suppose you have to generate a square wave of 66% duty cycle. If you have learned this program, that is, you have learned the method of generating delay using a subroutine, then you can easily modify the main program to get 66% duty cycle square wave. How can we do that? 66% is 2 by 3. So the waveform is, it should be high for 2 delay times and low for 1 delay time. So how will we modify the main program? After making the port pin high, we will call delay twice and then clear the port pin and call delay once. So that will make our square wave have a duty cycle of 66%. And suppose you are required to generate a square wave of 50% duty cycle, that can also be done using the same program. What should you do? You should modify the main program such that after making the port pin high, call delay once, then clear the port pin, call delay once. Repeat. So you will get a square wave of 50% duty cycle. So you can see that this program is versatile. You can make this program suitable for any duty cycle. So try to learn this program. Now let's look at one more aspect that we have covered in this program. This is the first time that we used a subroutine. So let us understand how a subroutine call works, and let's look at what happens during the subroutine call. So the yellow highlighted instruction, let us say that this instruction is being executed. A call delay, the first A call delay which is shown in yellow is being executed. And assume that it is stored at the memory location 2000. Then the A call delay instruction is a 2-byte instruction. The opcode of A call will be at 2000, and the assembler would have calculated an 8-bit value corresponding to the label, and that will be stored at 2001. So the next instruction should be stored at 2002. So A call delay occupies 2 bytes, 2000 and 2001. So the address of the next instruction will be 2002. So while A call delay, the one in yellow, is being executed, the content of the PC will be 2002. And what does this instruction do? It transfers program execution to the delay subroutine. So before transferring the program execution to the subroutine, 8051 will store the content of the program counter into the stack automatically. You can see that we have not used any push instruction that stores value into stack. 8051 will automatically do that. So how will it do that? It will store the low byte into the stack first, followed by the high byte. So the contents of the PC will be stored into the stack. After the storage operation is completed, the value of the program counter will be modified so that it contains the address corresponding to this label. So after this is done, the program counter will contain the value corresponding, the address corresponding to this label, delay. So let us say that it is equal to 3000H. So now the PC will contain 3000H. And how does the 8051 fetch instructions from program memory? It will fetch instructions from the memory location which is stored in PC. So the next instruction will be fetched from the memory location 3000H, and 3000H corresponds to this label. So the instruction that will be fetched next will be move th0, #0ffh. Then the program counter will be incremented, the next instruction will be fetched, it will be again incremented, and so on. So after the PC has been stored into the stack, PC will get a new value which is the address of the subroutine, starting address of the subroutine. Let's say that is 3000H. So once the PC has been modified to the new value, then which instruction will be fetched from program memory? It 8051 will always fetch instruction from the program memory whose address is stored in the PC. So the next instruction will be fetched from the memory location 3000H, and 3000H corresponds to this location, and this instruction will be fetched. And the program counter will then be incremented, and finally we will reach the return instruction. After the subroutine has been executed, we will reach the return instruction. What does the return instruction do? It pops the first 2 bytes of the stack into the program counter. When the return instruction is executed, the first 2 bytes of the stack will be popped into the program counter. The program counter will now be containing an address that is 3000 plus some value. These many instructions have been executed, so the program counter will have been modified to a value that contains the address of the instruction after RAT. It will be containing a 3000 plus something value. That will be replaced by the address from the stack when the return instruction gets executed. So stack is a last in first out memory structure. So the high byte will come out first, then followed by the low byte, and the value now in the PC will be 2002. The content of the stack will now occupy the program counter. So which instruction will be fetched next? Always 8051 fetches the instruction whose address is stored in the program counter, and the address in the program counter is 2002. So the next instruction will be fetched from 2002, that is this instruction. The second ACALL delay instruction will be fetched next. That is how 8051 switches to a subroutine and comes back to the main program. Thank you. Please learn this program very well for your exam. And in all the university question papers, there has been at least one program that generates a square wave or toggles an LED using timer. So it is a very important question. Make sure that you study this very well. You may find it difficult when you hear it for the first time. Please hear it repeatedly until you are thorough with it. And even after listening to this a few times, if you are unable to follow, please call me. Thank you.